In this video, we will go through a brief design exercise illustrating how to map a conceptual design into a logical design into a physical design. Generally, we follow these steps from a very high level. Step 1, do you need a computerized database? Well, in a course like this, you can assume that you do. We're not trying to trick you. Step 2, who knows how the database should work? Who is the domain expert? It's probably not you. It may be you if it's a database you're designing for yourself, or it's an industry you've worked in for a long time. But typically, the customer will provide one or more domain experts to help you along your way, or a systems analyst in your company will work with the domain expert and provide the design to you. Step 3, what do you want to store? What do you want to retrieve? Without question, the most important step. If you can't store what needs to be stored and you can't retrieve to meet the needs of the customer, you've already failed. That's why the domain expert is so important. Step 4, what storage model will you use? This drives how the schema is designed and how the tables are designed, if there are tables at all. In this class, we will be using the relational model because it's the only one we have. Step 5, we will take the information from step 3 and we will map it into tables. Tables have attributes. Tables and attributes have constraints and data types. At the very, very highest level, we provide a brief description of what the database does. If the database is extremely complex, this becomes problematic, but for us, for this example, we can do something a little silly. Your customer is the UC security office. They want to know what vehicle is parked where at any given time. They want to monitor their parking lot. They also want a history of what vehicle has parked where and when it was parked there. So they want a report telling them what happened yesterday, what happened last year. They will number the parking spaces and install a network of interconnected drones constantly scanning license plates and associate those with parking space numbers. So we're getting a little silly here, obviously, or we hope, obviously. The parking office will not be hovering drones over the parking lot 24/7. The drones are linked to your database through embedded software written by UC College of Electrical Engineering Co-op students. If you know any electrical engineering students, you know they can't write code. That's another attempt at humor. Nothing can go wrong. This is simply an illustration of how to create an abstract. Notice there is no computer jargon. There is no technical terms. This is simply a very broad description of what the database is going to do. Now we're getting interesting. UC Parking wants you to provide this report from the database. This is the holy grail. This is the pinnacle of what we do when we start a design. We have to get the customer to tell us what they want out of the database. If we know what they want out, we can decide what has to go in. Then we can decide if that information that has to go in is actually available from somewhere and how to get it in. Whenever you work with a customer, when you work with a domain expert, rule 1 is to get the reports, because that is what drives the failure or success of the database. What do they want to get out? Ask them for reports. Ask them for spreadsheets. What result, what purpose do they want the database to serve. Referring back to our list on the previous slide, slide 2, steps 1 and 2 are done for you. Step 1, yes, we do need a relational database. Step 2, the domain expert will be me in the UC parking office, because this is not a real world application and I will act as domain expert for you. Step 3, what things in the real world are we capturing? Well, I will tell you that we want a vehicle license plate entity, a parking space entity, and a history of vehicles and vehicle license plates and parking spaces, which will be somehow related together over time. To get to this point, we would have done many hours of meetings and discussions and design efforts with the customer, but that is not within the scope of this course, so we jump to this point and assume it's correct. I don't want to overthink these steps, because we're creating this as a practice example. It's not meant to reflect anything in the real world. It's meant to be interesting and a little bit silly. Step 4, what storage model will we use? We've talked about the things we want to store. We've defined the entities, the attributes of those entities. We probably discussed constraints. We've discussed relationships between entities. At some point then, and this is as good a point as any, when do we pick our storage model? By edict, by fiat, I will say we are using a relational model because it's all we have in this class. Step 5, things are starting to get interesting for us as database designers in this class. We get to design the schema using the attributes, entities, and connections between them that we've already been given. Our domain expert told us this: over time, a parking space will have many vehicles parked in it. Over time, a vehicle will park in many parking spaces. Now, as you get better at designing databases, you will recognize this is a many-to-many relationship that comes with practice. It's part of the job. This one is fairly straightforward because you've all used a parking lot. You've all been in a vehicle that parked in a parking lot, and you realize that a parking space gets used by many vehicles over time, and a vehicle will use many parking spaces over time. You may say to yourself, I always park my vehicle in the same parking space no matter what. I would never use many parking spaces. That's true, but you're a special case. You're an outlier. The point is, our database must adapt to the possibility that one vehicle over time will park in many different parking spaces. So you, as a consumer of one parking space forever and ever, are a subset or an outlier of this condition. Your systems analyst would recognize this as a many-to-many relationship, hopefully would communicate that to you, and you would implement this in your schema as a many-to-many relationship. Having gotten to this point, then, we can surmise that there will be a vehicle table, a color table, a parking space table, and a parking history table. And then we will connect those tables through foreign keys I will certainly agree that there would be other ways to solve this problem, and I will hopefully assume that you agree that we would have spent by this time a lot of hours in meetings and design discussions and emails back and forth and documents discussing how to model this data, how to store it, how to retrieve it. But we skipped over those steps because they are not part of this class. Moving on from the conceptual design, step 2 is the logical design. We've got everything we need from the customer. We realize there are 4 things to be represented in the database, if you will, call them entities. A vehicle entity, parking space entity, a parking history, and a color. This is where you start getting busy in this class. You will be creating logical designs for me. You will be normalizing logical designs once we get to the concept of functional dependencies and determinants, which we haven't done yet. But this is something you can do now. You can define these entities using the constraints, using the rules defined here at the bottom of the slide. Whatever the natural key is in each of these entities, underline it. Don't put in any surrogate keys yet. Don't assign any database type, any data types yet. Don't build in any foreign keys yet. And use common attribute names to infer connections or joins between the tables. There are many tools to do this work. We are simply using Microsoft Word or a PowerPoint slide. But there are high-powered tools that will take your conceptual design and map it into the rudiments of a logical design, and then take that logical design and map it into rudiments of a physical design. We don't have those tools, and we are not using complex problems that might require those tools. So doing this by hand teaches us how it works. Then when the tools become available, we have a great understanding of what's happening under the hood. Once we've finished our logical design, we wrap that into the conceptual design, and that becomes a physical design, which is a schema. At that point, you can see we're deciding on data types. We're adding surrogate keys to all of our tables. That's one of our design rules. Always use surrogate keys as primary keys. We're dropping in foreign keys when there's relationships between tables. We're adding constraints to attributes. And then we're implementing that in whatever DBMS we decided to use. Before you continue on, open the naming conventions document on Blackboard and review it thoroughly, because I'm going to create some tables and I'm going to use those conventions. I expect you to use the same conventions. They are not the ultimate conventions. They are not perfect. They are not a solution to every instance, but we will use them so we all speak the same language. And so when you look at my tables, you know what to expect. And when I look at your tables, you know what to expect. When you go into the real world and you begin designing schemas and implementing physical databases, you may use some of these rules. You may be given a set of rules, a set of conventions, a set of requirements by your employer. You should use those. These are for the purposes of this class. I have used them extensively in my professional career. They have developed over time. I have many databases in production at different clients, and I have found these rules to be very useful and effective. But they are not the only rules. So do not become wedded to them, and do not fight Do not resist when you are given other sets of rules to follow. The next thing I will do is leap over to SSMS and begin the implementation process of our logical design. We're making a lot of assumptions here, remember, because we don't have a complete conceptual design documented. But since that's not part of this class, we can impose those things on you, and then we'll be fine. The general rule to follow is that if you don't know the answer to something, ask. And if I don't provide it for you, I'm usually leaving it up to you to decide. In this case, I am telling you that there will be 4 entities, which almost always map to 4 tables, and you will follow our design rules. Here are the design rules taken off of Blackboard. We want to be consistent. If we all speak the same language and we all use the same rules, we have a lot easier time deciphering each other's tables. Here is SSMS. I'm connected to the classroom server. I am going to use a database called Parking Lot 3060. You should use your personal database as you follow along. You can still name the tables the same way I do. You just don't have a separate database in which to put the tables. Remember, later on, if you had the need, you could migrate those tables to another database. That would not be a problem. So where you put them now is not a big deal, except the only place you have permission to put them is in your database, not in the master database, not in this Parking Lot 3060 database. Let's do the simplest one first. Let's just do color. And again, in the logical design step, typically an entry in the logical design will map to a table. Sometimes not, but in this case they will, because that's the way I laid it out for you. The color table, all it has in it in the real world is a color. But we're taking that logical design and mapping it to a physical implementation, mapping it to a table, so we need to provide some more information than just a color. If you look at my requirements, requirement 1, do not use spaces in your symbol names. Symbol names meaning table names, attribute names, key names, index names. We don't put spaces in things, and there's a good reason for that when you start writing scripts, because you don't have to think about delimiters to hide the spaces when you use these names in scripts. It just makes life a lot easier. You can use camel hump notation to name things. It's just as easy to read. You've been doing this when you write code in Java or C# or PHP. You don't have spaces in those symbol names. There's no reason to put spaces in these symbol names. Now, I know this will cause some conflict in some areas. Some developers are okay with spaces. And I'm not saying this is a law. This is not a constitutional amendment. This is just the way I do things, and this is the way I want you to do things. What should the table that contains colors be called? All our tables will start with the T prefix, lowercase t, and a table name represents one row in the table. The table name is not plural. If it's the color table, we will call the table T color. Now, I don't think it will let me save it yet because I haven't put anything in it yet, but we will call it T color. Every table will have an auto number, integer, primary key. You will take the table name, in this case color, and append to that ID in capital letters. In this case, color ID. The data type is int. If you make it the primary key, it turns off allow nulls because the primary key cannot be null. And immediately change the identity specification to yes, leave the increment at 1, leave the seed at 1. That means the table will have as its first primary key in the first row added to the table a value of 1. The second row will be 2, 3, 4, 5, and so on. That is our design rule. That is rule 6 as described here. Every table must have a natural key. The natural key is something that exists in the real world. In this case, we don't have a lot of choice. If you look at the logical design, there's only one other attribute in this table, which is color. We add another row, color. Now we have some ambiguity because we do not know how long a color should be. We could shotgun this and pick some wildly humongous number with being reasonably sure that no color will be 500 characters wide. We're not going to put a lot of thought into this right now because we just don't have enough information to solve the problem correctly. We can use our intuition, we can use our common sense, and we can say a color is probably no more than 50 characters. Since it will be a key, since it will be the natural key in this case, we will uncheck that. Now let's immediately make that into a key. So right click, indexes and keys. The primary key has already been added for you. You don't have to change the name of that. I just leave it. Select add, and let's pick the color column. And then let's say what kind of thing is this. Let's call it a unique key. Again, I don't rename this. You can if you like. Click close. All right, we have a table with a surrogate primary key and another candidate key, which is the natural key. We haven't saved it yet. Our naming convention is a lowercase t followed by the description of one row in the table. It's not colors, it is color. Again, other places you work, other databases you see will use different conventions. This is our convention. Now we have a table. You may need to refresh this to get the table to show up. You can actually add information to the table. You do not add anything to the color ID. It is automatically maintained for you by the database engine. The first row will be 1. The second row will be 2. If I try to duplicate a color, it will fail because I already have a red and I created a unique key on the color column. And I get this. And here is where you must slow down, carefully read the error message, and figure out what the problem is. Don't give up, don't run away, don't go watch TV. Take your time, you may have to Google it, but you can figure out what's going on here. It says cannot insert duplicate key, and it tells you the duplicate key is red. What can I do? Press escape. And that attempt goes away. Let's put in green. Notice that 3 is gone. Notice that the primary key, the color ID 3 is gone because I already tried to use that with red. And even though it never showed up in the table, it did reserve that key value. The color ID, given that it is an integer, can go up to 2 to the 31st minus 1 or over 2 billion. It's unlikely we'll have 2 billion different colors in our table. So it's okay to drop or use and discard an ID once in a while. That's not a problem. Let's go back to our design. We have a parking space number table, which has the same general or same structure as the color table. It just has one attribute. So we can follow the same rules to create that parking space table. This isn't quite right. I left out some consistency. Now I'm happy because the table name is the same as the attribute name, which will become the natural key. So the table is called parking space number. The natural key is called parking space number, and now everything matches up. Notice also that the parking space number appears in another table as part of a key. We can see that there then is a foreign key primary key relationship between those two tables. So let's go back to SSMS and let's create another table. New table. Parking space number ID. It's an integer. It can't be null. Make it the primary key. Add another field. We're a little bit concerned now because we don't know the data type for a parking space number. Does it have letters? Does it have only numbers? Does it have weird symbols? Let's just, for now, since we don't know any better, we'll just leave that as a character field of 10. Let's make that into a candidate key. And I forgot to make this an identity field. This gives me a primary key, which is a surrogate key, a parking space number ID. This gives me a natural key, which is a candidate key of parking space number. And then I save it as T parking space number. And you can see the consistency throughout, using the same names to represent the same things throughout. It's a very simple template to follow. It creates very effective consistency for simple and moderate tables. When the tables get more complex, sometimes this falls apart a little bit, but for the most part it works. Click OK. I have two tables. And those are my easy tables. Now I have the vehicle table. The vehicle table has a composite natural key, license plate, and state. And it also has a color. And since this color is the same name as this color, and since this color is a key in another table, that implies, or we may infer from that, that there is a foreign key primary key relationship between those two tables. Let's create the vehicle table. I'm going to grab the word vehicle. I know I will be using it in the table creation. New table. Vehicle ID is an integer. Make it the primary key. Change the identity to true. I need license plate and state. All of a sudden I forgot how to type. Now what I don't want you to do is put a space in there. Remove the space. We have an issue. How do you represent license plates? How long can they be? What can they contain? For the purposes of this exercise, we will assume that a 10-character wide field is sufficient to hold a license plate. Certainly we would be doing more research than this in the real world. Since it will be part of a key, we will not allow nulls. The state. We need the state. Now, we have two-letter abbreviations for all the states in the United States. We will assume that this database is only going to encompass license plates from the United States. Again, that would require more research. In the real world, for the purposes of this exercise, we will make that assumption, turn off nulls, because these two attributes together will become the natural key. Remember, they are underlined together. Therefore, they are together taken as one natural key. Let's immediately put in that key. Go to Index and Keys, select Add, change the type to key, bring up the columns dialog, and let's add license plate and state. Now I have my natural key. And let's save this table. T vehicle. But wait, there's more. I have the color. Now the color, because of the name of the attribute and because it matches the name of a key in another table, needs to be a foreign key. The foreign key should be the same name as the primary key to which it relates. This makes life so much easier. If I see COLORID, I know that that is probably a foreign key to the color table. This has to be an integer because the data type of a primary key is an integer. It is not an index specification. We do not change the identity property down here for a foreign key. But we can go back in and define the relationship between this table having the foreign key and the color table having the primary key. Right click, relationships, add, tables and columns. Where is the primary key? Well, it's in the color table, which is beautifully obvious because of the way we named the attribute. Once we pick the color table, we can tell it what attribute in that table. That's beautifully obvious because of the way we named the primary key in the color table. The foreign key is in the vehicle table because that's the table we are currently working with. And the corresponding foreign key in the vehicle table is color ID. Using our conventions, things match up beautifully. We were able to do this in just a few seconds because we're all speaking the same technical language by following our conventions. There's more to this that we'll talk about later. If the value in the color table is deleted, what do you want to do with corresponding rows in the vehicle table? If the value in the color table is updated, what do you want to do with corresponding records in the vehicle table? We'll leave that alone for now. Those are fine. Close. We can decide whether or not a vehicle can have a color. Is our database going to force the users to provide color for all vehicles? I'm going to say yes. Again, that's a design consideration provided to you by the domain expert, but at this point we're just going to wing it because we don't have a conceptual design and we're just doing an illustration. Remember, the star next to the tab means that this data has not been saved yet. Also remember that if you start messing with keys, foreign keys, natural keys, if there's data in the table, you may not be able to save the table design because you may have created a conflict. So it's important to do all this before you start putting data in the table. This message is fine. Click yes. Let me show you something that we as designers often have to do to make our lives easier, and you may want to do this in your instance of SSMS, tools, options, go to designers, go to table and database designers, and if you uncheck this, you will be able to make changes that you could not otherwise make. Sometimes a table has to be dropped, meaning deleted and recreated, to implement a change that you made to the table design. Without getting into too much detail of when that happens, because we are in our sandbox, because we're not using production data, we don't have really anything to lose. We uncheck this box. That lets us fly through the design in a lot easier ways than having to go back and think about what we're doing. So in the real world, if you're working with production data, it's probably safe to, it's certainly safer to have that checked. But in this pretend sandbox world, uncheck that and you'll have a lot easier time changing your table designs. Okay? And once you make that change, it sticks for all the databases that you mess with. So it is an SSMS configuration setting. It's not specific to a particular database. There's our table. We have everything except parking history, right? The parking history table has a reference to vehicle, okay? And it has a reference to parking space number. So we know that there are two primary keys, two foreign keys in this table. There is a foreign key into the vehicle table. There is a foreign key into the parking space number table. I will leave this table as an exercise for you to create. I encourage you to do that. And once you have all four of these tables created, I encourage you to populate these tables. You should have done a little bit of this in 2060. If not, let me know and I can give you some guidance, but you should be able to figure it out. Populate the tables with foreign keys and data, and then write a view. Now, this is what you did by hand in 2060. This was much of the thrust of 2060, but I encourage you to use the View Designer at this point. One, because you get good experience with it, and two, because it's a lot quicker than typing in these scripts by hand. Now, if you're a wizard at creating views and you feel like it's something that's just in your DNA and you don't want to use the view designer, I still suggest you use the view designer at least a little bit, because you can see how SSMS builds the same kind of view that you would build, and you will learn some things about what these queries look like. When you're finished, you should have 4 tables. You should have a parking history table with 2 foreign keys, 1 foreign key pointing to the vehicle table, 1 foreign key pointing to the parking space number table, and then you should be able to join all 4 of these tables together to create a useful view that looks something like this. That's the reason why we do what we do, to retrieve data from the database. Putting it in is great, designing the database is great, but unless we can pull it out in meaningful ways for the customer, then we haven't succeeded at anything. That view is our ultimate goal. The view won't look like this. It won't be nearly as pretty, but prettying up the results is not the job of the DBA. That is the job of a user interface designer or an application developer. So don't beat yourself up if it's not this pretty. Notice that the date time out can be empty. So when you design that parking history table, make sure you allow that field to be null. That makes sense with the real world, because the car could still be parked in the parking space. It hasn't left yet. It does not have a date time out value associated with it. That brings us to the end of this video. Remember, go back and implement the parking history table, populate the tables with a little bit of data, and write a view, and you will have successfully completed this exercise. Thank you.